Hello everyone, we're Group 2 from SPCS. I'm Rebecca.
And I'm Sherry. And I'm Nicole.
The goal is to use the ISS speed of 7.66 km per second to prove that the GSD equals to 0.126. Given the pixel width, focal length that is constant, we can find the distance between the ground and the camera.
To find the ISS speed, the results collected with the Astron Pi camera is then improved with the results we have from GSD. Earth photographs taken by Astron Pi camera are compared over time. Common ground features are tracked between consecutive images to measure pixel displacement. This pixel shift is converted into real ground distance using camera parameters such as focal length, sensor size, and ISS altitude. Dividing the ground distance by the time interval gives the ISS speed. This method is simple, but it includes errors caused by camera rotation.
Hence, it is improved by calculating GSD to compare with the result found by taking pictures with Astron Pi camera. The pixel shift caused by the movement of ISS is calculated in order to find the ratio of the pixel shift and difference in the ground distance. The correct pixel shift is then converted to the ground distance with the aforementioned ratio and divided by time to calculate a more accurate ISS speed.
We have made some assumptions, and they are GSD calculation, speed calculation, technical, usage, and hidden implicit assumptions.
The analysis began with processing calculated data generated via code, which included the time difference between each photo pair set to a consistent 5-second interval, pixel displacement, average feature distance, and real-world distance. Leveraging this foundational data, the final output results were auto-generated, including the automatically calculated ground sample distance known as the GSD, individual speed derived, overall average speed of the observed objects, and the pixel width of the input images, all of which collectively formed the core quantitative findings of the experiment. Then let's talk about the packages used. The EXIF package reads the time each photo was taken so we can find the time between the shots. And then the CV2 analyzes the photos to find matching features and calculate how much they moved in pixels. The PicCam0 takes 42 photos automatically, one every 5 seconds. And lastly, the Log0 logs errors to a file to help fix problems if the code crashes.
Functions used for Astron Pi camera is mentioned below. Firstly, we have to extract image dimensions and get the time difference, and then we convert the data collected to the format of OpenCV. Then we compare and sort the similarities between pictures to find matches, and at last we locate the matching coordinates. Functions we have used for GSD are included as below. From the photos metadata, we get the basic information needed to calculate the GSD. And then we use those data to find the GSD with the GSD calculator using the ratio of pixel shift and the difference in ground distance.
At first, coding seemed like an impossible mission for us. Yet, fueled by our team spirit, perseverance, and the dedication of every group member, we ultimately succeeded. When I spoke with my teammates, they shared that grasping the coding process was exceptionally challenging. So, we came together to break down the code step by step, and this approach proved incredibly effective. One member even said, "This is the first time I've understood coding this clearly." Understanding the concept of GSD was another tough hurdle too. With our tutor's guidance, though, we carried out a simple yet crucial experiment, which helped us gain a far better grasp of the idea. In conclusion, the Astron Space Lab competition not only taught us a great deal more about coding and astronomy-related knowledge, but also honed our teamwork skills. This system struggles in simple scenes and is distorted by poor feature matches. It assumes perfect camera movement and ignores rotation or tilt. Since GSD is calculated only once, any change in altitude makes speed results inaccurate. Thank you.